Hello and welcome to this webinar on instant and accurate capital cost estimation of static equipment. Today's webinar will begin with an overview of autopipe vessel, followed by an introduction to the cost estimate module of the product. Then the first topic that will be covered would be creation of cost estimate from an existing design model file, providing an overview of the cost estimate module, followed by creation of cost estimate from scratch. In the second part of the webinar, we would look into cost estimate module customization with task hours calculations modifications and material and hourly rate customization. In the last part, we would look at how the cost estimate module can be leveraged to optimize the cost of capital equipment and reach quicker design decisions with the goal of reaching a safe and cost-effective design option. Autopipe vessel powered by Microprotol is a software that can design virtually any type of pressure vessel, air cooler, heat exchanger, and tanks to most of the major global design codes. One of the strengths is the ability to import thermal design data from HTRI, Aspen, ProSim, and Honeywell, as well as exporting to the major CAD software and plant design softwares like PDS and AutoCAD, SolidWorks, MicroStation. The software is ideal for both EPC companies and also equipment design and fabrication companies. There are several advantages of the software, including maximizing productivity of skilled engineering resources, supporting a global market, and improved collaboration across distributed project teams. Many large EPC oil and gas owner-operators manufacturing companies use autopipe vessel for their static equipment design and analysis need. Some of them are mentioned here. After completion of design, the model from autopipe vessel can be exported to MicroStation and AutoCAD for 2D drawing and 3D model generation and creation of 3D model in SolidWorks. Autopipe vessel supports several American as well as international codes and standards. The American codes include ASME Section 8 Division 1 and 2, TEMA standard for heat exchangers design, API 650 and API 661 for storage tanks and air cooler design respectively, and EJMA standard for expansion joint design. The international codes include French CODAP, British PD 5500, German AD Markblätter, Russian GOST, European EN 13445, and others, and recently implemented Chinese GB 150 code. We will begin our webinar today by taking a look at the cost estimation module now and how to create the cost estimate of an existing design model. The cost estimate module can be launched from within the main program by clicking on the $sign as shown. In this exercise, a vertical distillation column has already been modeled and analyzed, and the cost of the same will be estimated. There is a tutorial available under Help in the module to guide users on how to use and customize this module. The first step to perform a cost estimation is to select Preference under File and select the correct .cfg or config file from Estimate Configuration File section. There are two options to select from. The param.cfg is to be used for SI units and the param_us.cfg for US or imperial units. The user can copy and rename the config file of choice to customize it. Multiple config files can be created and configured as necessary and can be used appropriately. Following the step of specifying the configuration file, a new file needs to be created by clicking on Create a New Item File icon, which leads to two options: to use an existing file or to estimate from scratch. Here the option from Existing Autopipe Vessel File EMVD is selected. This opens the option to select the desired file which has been modeled and for which the cost estimate needs to be run. File New One is selected here. Once the file is selected and opened, there are two lists that appear. The one on the left is component library called the components code list, which lists all the components in the library. The one on the right is the bill of material, which lists the components imported from the model file. The program automatically extracts all the model information, including the component list and details of every component from the design and analysis module. Let's take an example of the shell component tag 31.07 in the design module. Going back to the cost estimate module, it is seen listed under the bill of material of the project. Double-clicking on it opens the component dialog box which states the material class, symbolic name, diameter, joint efficiency, length, thickness, etc. all are imported from the model file. The cost estimate individual component dialog box has three sections. The top section lists the dimensions of the component. The second one at the middle states the tasks to be carried out to produce the component. The cost estimate module performs detailed calculations of every step of the manufacturing process to arrive at the accurate cost, and the various tasks including engineering, handling and cutting, roll and prepare, grind and back gouge, etc. are listed. The third section at the bottom is for the component cost input. For example, if it is a purchased product of known cost, then the same can be input for consideration instead of the program calculating its cost. The transfer of the model information from design to cost estimate module is automatic without user intervention. On the top left is the component properties dialog box in the design module, and to the bottom right is the cost estimate module. After the creation of the component list, the user needs to click on the default material rate icon and review or modify the material rates. Observe bottom left, the forging item is selected and the unit price is modified from 4.73 to 8. Clicking on apply makes the change go through. The input of the material rate is generally the only manual part of the process where user intervention is required, since material costs are not constant and varies with time and location. The unit price can be selected from kilogram, meter, or simply unit. Observe that the currency value is not mentioned, so user needs to maintain the same currency throughout the project for consistency, as well as for any labor rate or material rate customization, a topic that will be covered shortly. Once the material rate is input, clicking on the cost estimation bill of material icon generates the cost estimation and bill of material in Excel file format. Shown here is the bill of material sheet of the estimate file listing the components according to the item tags, descriptions, materials, ID, OD, length, thickness, the freight weights, raw weights, and the computed cost. As an example, item tag 31.06 represents the shell or barrel section with OD 974, length 300, thickness 12 mm. The freight weight is 85.41 kg calculated directly from the dimensions, but the calculated raw weight considers all the machining allowances etc. and is 199.28 kg. The material rate is 1, so calculated material cost of the component is 199.28 kg. The cost estimate summary sheet lists the manufacturing costs, engineering inspection costs, subcontracting costs, inspection subcontracting costs, and material cost, all of which are finally summed up to obtain the total cost. Let's take a close look at the manufacturing cost summary. In the left image, under Global Estimate Cut and Prepare, the total hours shown is 241.9. This is the value that comes from the summation of all the cut and prepare or C&P hours for every component in the model, as shown on the bill of material to the right. As an example, the barrel component tag 31.05 will require 2.06 hours to cut and prepare. Cone 30.23 requires 3.9 hours. Adding all the cutting and preparing hours yields the total number of cutting and preparing hours as 241.9, which is reported in the global estimate. Likewise, for roll and prepare, the total computed hours, which is 15.87, comes from the bill of material summation of all components, roll and prepare hours, as well as for all the other manufacturing tasks. Likewise, in the global estimate summary for materials, the various categories of materials, for example plate, forging, tube, pipe, bolting, are aggregated from the bill of material. As an example, the total weight of plate reported in summary is 4370.88 kg, which is obtained from summing the weights of the plates in the bill of material components. The summation of the different cost categories produce the final total manufacturing cost. A margin can be applied as well as a percentage for obtaining the sale price. This is very useful in the event of budgeting or performing capex analysis of your project where you need to procure equipment. There are obviously instances where the user may not have the need to design the vessel to obtain the cost estimate, but want to quickly compute the cost of either individual component or whole vessel based on given component dimension and materials. In previous example, the option from existing autopipe vessel EMVD was selected. This time the option manually from scratch would be selected. Once the component code list is displayed, double-click on a desired component, for example 20.05 barrel, which then adds it to the bill of material. The barrel dialog box opens. Since this is designed from scratch, manual entry of all fields like dimensions, material, joint efficiency, etc. is required. Once the component description is complete, the material rates are reviewed. In this example, we will select the plate material and change the rate from 1 to 2.5. Let's assume the currency is in US dollars, so plate material rate is $2.5 per kilogram. The estimated cost of the component is instantly calculated as $3905. This feature of individual component estimation without performing whole vessel analysis is very helpful for quickly estimating components or equipment cost and does not require the user to learn the specifics of vessel design and analysis. In the foregoing section, we saw how to quickly calculate the equipment cost either from a model file or even for individual component from scratch. In cost estimation, it is very important for the user to customize certain fields like material and labor rates, which widely varies by location in one organization to another. Also, the user may have their own methods to calculate the hours required to perform a certain task. In this section, we will look into the customization feature of the estimation module. We have already seen how the param configuration file can be selected from preference. In case a user is going to customize the configuration file, it is highly recommended that the customization modifications are made to a copy of the config file. As an example, in this screenshot, a new config file was created by copying the param file with a name being given as param-project1. Also, the user can create multiple config files and customize them individually. For example, there may be 3 different config files for 3 different global locations of a manufacturing company, with each one being assigned the appropriate material or labor rates. The customization option can be accessed by clicking on the gear symbol icon as shown. The module is not password protected, hence just clicking on OK in the Customizable Files Management dialog box opens the Estimate Configuration File Properties dialog box. There are 4 tabs in this dialog. The first one lists all the components as in the component code list. As an example, clicking on the 20.05 item displays the task list required to make the component. Further, each task can be individually clicked to display the options list, for example, roll and prepare or subcontract the task. Click on calculation method at bottom right to view the calculation details. We will next take a look at how the rolling and preparing task hours calculated. The task duration is calculated from a parameter z, which is a function of the parameters diameter and total length. This relationship is explained from a list of data points represented by range of diameter and length and the corresponding value of the parameter z. Z value is interpolated or extrapolated by the software. Finally, the total duration is calculated as product of the computed variable z and number of plates and quantity. The last variable in the above calculation is the parameter whose value is passed on as the duration, which is represented here as zf. Let us now consider a situation where the user wants to modify the previously discussed roll and prepare task by including some additional equations and variables. Assume a hypothetical case that the project the user is working on involves fixing of some appurtenances with a certain width and length on the rolled shell, which would require some surface preparation, like for instance polishing. Let there be different levels of polishing required, so the task duration would be a function of the level of polishing, the number and size of the attachments. Hence, we need to create additional input variables which does not exist currently, like levels of polishing, number of attachments and size of attachment. Let's go back to the configuration dialog box. Select 20.05 item, select roll and prepare under task list, and again select roll and prepare under options list and click on calculation method. The 3 new input variables can be added as follows. The symbol LV is entered in the white space at the bottom of the variables list section shown at bottom right. Then tab and the text level of polishing entered followed by enter. This will add level of polishing variable denoted by the symbol LV, which can be used as an input variable in the calculation function. Likewise, the other 2 variables, number of attachments NM and attachment size SZ, are also entered. Finally, the equation is modified reflecting the introduction of the 3 new variables in the output variable, ZF or the task duration as shown. The old component dialog did not have the 3 variables, but the new one after the preceding customization now has 3 additional fields for the new variables. The user can now enter values for the 3 variables in the newly introduced fields. Now compare the old versus new estimates. The old estimate rate for roll and prepare was 0.82. The new estimate has been updated with the new equation, and the revised rate reflects the same as 10.82. The estimated cost consequently is updated with the revised cost of manufacturing from 3905.02 to 3958.04. Similar to our previous exercise, let's look at how to customize the material rates. As we saw earlier, the material cost can be updated every time a cost estimation is run by using the default material rate option as shown here. However, it may not be feasible to always change the material rate manually, or perhaps the user wants to create separate configuration files with different material rates. The material rate can be changed globally for a particular config file, just like the task hour rate modification that was performed. The material rate can be modified from the Estimate Configuration File Properties, second tab called Rate and Time. The first column in this tab consists of the material list and density, which will be used for weight calculations. The second column is Product Form List, which lists the material rate. Observe that the rates for plates and forgings are 1 and 4.73 respectively. We will change the rates of carbon steel to 2 and forgings to 6. First step, Select plate and double click. Change the value to 2 and hit enter. The plate rate is changed to 2 as shown in the image to the right. Following exact same steps, change the rate of forgings to 6. The rate changes can be confirmed from the default material rate table in the main cost estimate window. Let us now review the labor rate customization. The labor rates can be obtained from the cost estimate report global estimate in the manufacturing cost section under rate column as shown on the left image. These rates come from the rate and time tab of the customization module, that is the estimate configuration file properties window as shown on the right. The third column in the image to the right shows the task list which listed hourly labor rates. We will modify the labor rates next. Following the steps involved in the material rate modification process in the preceding section, the labor rate can be changed by simply selecting the task, for example welding as shown here, which activated that task in the input field at the bottom right, and click OK. Change the rate to 50.0 and hit enter. An important thing to note here is to enter 50.0 and just not 50 to make the change take effect properly in the final calculation. Let's now go back and rerun the estimation. As expected, the hourly rates have all been updated in the new estimate report. Cut and prepare rate updated to 75, all other fields updated to 30 except engineering to 50. Here is a comparison of the old versus new labor rates. The manufacturing cost has significantly increased with labor rate revision from around 4,400 to more than 9,500. The old estimated cost is 7,526 and the new cost is 15068 due to the change in the labor rate and material rates shown in the foregoing slides. What we got from the change in the labor rate is a clear visibility on the overall cost impact due to a change in labor rate. If the user is working on a large project with several equipment to run estimates, then it is not practical to change the labor rates and material rates for so many tasks and materials. It would be time consuming and prone to errors. Instead, the easiest approach would be to perform a global rate configuration and save those as separate configuration files and apply the appropriate configuration files. In fact, an evaluation on the most cost-effective solution by a thorough analysis of material and labor cost options can be performed, a topic that we will cover next. Having covered the fundamentals of cost estimation and customization of the same, we will now look at some real-world scenarios where the design optimization and cost reduction can be performed using the cost estimation feature. Before we move into the cost optimization, let us look at the design optimization capability of the product. In the main Vessel Properties dialog box in Autopipe Vessel, there are two options, Design and D-Check. The design option, which is set as default, is one where the software performs the complete design and optimizes every pressure retaining component based on basic user inputs like length, diameter, and design conditions. At the end of the calculations, the software alerts the user with errors and warnings for necessary action. The D-Check option is used to check an existing design in which the software does not optimize the design but performs only code checks and calculations to ensure the design meets code requirements and alerts the user regarding any deficiency with error messages and warnings. Let's take a quick look at the optimization logic of the software. First, the internal and external pressure cases, hydrotest pressure calculations are performed and thicknesses determined, followed by vibration period determination and calculations for wind load conditions. If there is overstress, component thickness is increased, else it proceeds to calculate for seismic load case. If the equipment is a vertical column and there is a specified maximum column deflection to be maintained, the software checks for that, and if that condition is satisfied, it proceeds to seismic load case calculations. If the seismic calculation fails, the thicknesses are revised, else it proceeds towards nozzle reinforcement check and performs necessary optimization action for nozzle design. Finally, the calculations for base, anchor, saddle, etc. are performed and the report generated with the load case calculations. So why do we need to optimize the design of pressure vessels after all? In a typical petrochemical complex or chemical plant, there could be more than 100 pressure vessels of various kinds. The static equipment, which includes pressure vessels, heat exchangers, tanks, air coolers, etc., constitute a major portion of the plant's initial capital investment. Particularly equipment subjected to extreme service conditions including very high temperature, pressure, corrosion and erosion like chemical reactors, etc., fluidized bed reactors, which are primarily made of high nickel alloys like Hastelloy, Incolloy and other heat resistant alloys, may cost several $1 million a unit because the material of construction is very expensive. In fact, they are typically one of the most expensive single piece of equipment commissioned in any plant. Hence, besides safety and durability of the equipment, cost reduction of static equipment including pressure vessels is very critical. Over-designed equipment or equipment not optimally designed translates directly to increased capex and longer break-even periods for investors. Optimization is also essential for material in stock or short delivery requirements. Now here is a case study that discusses how in design phase, common assumptions by the designer may lead to higher final cost of equipment and how this can be easily avoided using autopipe vessel. Shown here is an example of a horizontal vessel with a few nozzles. While deciding to select between nozzle with reinforcement pad and self-reinforcement nozzles, the nozzle with re-pad was specified by the user, since self-reinforced nozzle usually costs considerably more than regular nozzle due to more material and heavy forging used for the same, whereas usually a nozzle can be constructed of pipe materials or even by plate rolling. The understanding was that this would keep the overall cost of the equipment low due to lower cost of component. The total estimated cost was approximately $36,000. The same equipment now with self-reinforced nozzle, interestingly, was found to cost significantly lower at about $32,000 than the option with re-pad type nozzle, which is counterintuitive since self-reinforced nozzles cost more. The reason for more than 11% cost reduction was the elimination of cost of pad materials, welding, machining, and all the associated labor costs in this particular case, which are incurred in the re-pad option. Therefore, the actual estimated cost can sometimes be counterintuitive, and it is not possible to decide between various design options unless the estimated costs of all possible cases are individually analyzed. This would lead to better decision making and reduce total cost. Another case study is presented here, which talks about the effects of having a stiffener for external pressure design on the vessel cost. The example from case study 1 is considered. In order to eliminate the need of the stiffener, first, the model is made without stiffener by unchecking the option in the Vessel Properties tab as shown on the left. In the Component Properties dialog box for the transition cone, the knuckle radii for the large and small end of this cone are specified. The cone plate thickness is computed equal to 15 mm and the total cost is estimated at $22,000. To compute the cost of the equipment with stiffener rings, the option for stiffeners is enabled as shown on the left, and the knuckle radii are removed and the analysis rerun. As we can see in this case, the cone thickness is significantly less and is the same as the shell thickness for the whole vessel at 6 mm. The cost is likewise reduced by 12% to $19,425. The cost reduction is 50% due to material reduction and 50% due to labor, machining, and welding cost reduction. Material cost calculation is simpler, but calculation of accurate labor, welding, machining costs are much more complicated, which autopipe vessel performs to a high degree of accuracy. The cost of material can have significant impact also and can further increase the difference in cost for various design options. As seen in the preceding case study, the same equipment but using stainless steel this time is now evaluated for the external pressure options with or without stiffener rings. The cost is significantly reduced by 29% using stiffener, and this difference is much higher than the carbon steel case. Let's talk about optimization of body flange design. Body flanges can be a very expensive component of a pressure vessel, particularly if the material of construction is expensive, for example nickel alloys or stainless steel. Hence, performing an optimum flange design is critical for a cost-effective solution. Autopipe vessel flange design module offers several optimization methods, for example EN 13445 Annexure G with compression rings, loose and bolt tensioning options. There are 4 options available for optimization based on hub stress and gasket circle reaction optimizations, and also another design method based on bolt load, namely design full or control bolt load. Shown above are the results from a case study on the design of a body flange using the hub stress and gasket circle reaction based 4 optimization methods available in autopipe vessel. In summary, one can easily observe how much difference in cost each of the methods can result to. Options 2 and 4, which are the higher cost options, lead to a much more safe and conservative design with significantly reduced hub stress but with 40 to 55% cost increase. Options 1 and 3 result in more compact flanges with smaller hub length and flange diameter but at the cost of higher hub stress. Hence, the optimization method provides a valuable iterative approach to arrive at the most optimum design based on the cost versus performance criteria. In closing, I just want to draw your attention to a great resource for anyone wanting to learn more about the Bentley pipe stress products. Our YouTube channel has a variety of videos covering all aspects of our products, and more are being added each week. So if you're interested to see what's new or how to use a certain feature, subscribe and search the Bentley Pipe Stress Analysis channel. And if there is something you wish were covered but isn't, please drop us a line. We are always looking for ideas for additional content. The Select Connect edition was introduced in April 2017, and it is the most significant enhancement to Bentley's Select program since its inception. Select Connect edition continues to provide comprehensive coverage for your Bentley perpetual licenses, but now offers every subscriber the option to also equip their teams through quarterly term licenses. Applications covered under Select can be pooled so that they can be shared, and you can exchange titles once a year through portfolio balancing to adjust your changing project requirements. Most significantly, we are introducing Select Connect services, new Azure-based services that deliver comprehensive learning, mobility, and collaboration benefits, now included with your Select subscription. So you can now take advantage of these Connect services. Adaptive learning services. Access all Bentley learning content. Master use of Bentley applications through personalized in-application contextual learning. Personal mobility services. Individuals work anytime from any place through Bentley's apps. Project-wise connection services. Teams securely create, share, and deliver data and documents and review project status and performance. Go to connect.bentley.com today to get started. With this, I would like to end the webinar. Thanks for watching.